Cool. So this week we have our own Nikhil. We'll talk about fully adaptive decentralized MA-ABE, simplified, optimized, ASP supported.
Okay. Thank you. So glad to meet you all after a long time. Yeah, I'm Nikhil. This is joint work with Pratish and Junichi on multi-authority attribute-based encryption. And this is going to appear later this year at EUROCRYPT. And happy to present this work to you guys. Okay, let's start with what is attribute-based encryption. It's a generalization of public key encryption, which allows for fine-grained access control over encrypted data. So in this scenario, consider that CMU holds the public key and master secret key of the system, and anyone can encrypt a message with respect to a policy, such as CS department and professor, and send it over. And how can the users access such a message? It's as follows. So users control some attributes. Suppose a user has attributes CS department and professor, then it can request the central authority, which is CMU in this case, to issue a decryption key for these attributes. And another user with CS and student can similarly get decryption key and so on. Now, what the system supports is as follows. So if the secret key along with the attributes satisfy the policy, then the user should be able to decrypt the message. In the other case, the users should not be able to decrypt message on their own. And more importantly, ABE requires the following kind of security. It should prevent collusion between users who are unauthorized to decrypt. For example, if consider this user 2 and 3 who have attributes which on their own don't satisfy the policy, but their joint attributes do satisfy the policy, the CS department and professor. So even if they try to combine their key material together, it should not be possible to decrypt the ciphertext. While ABE as a primitive has seen a lot of success in both theoretical and applied cryptography, there's one big downside of ABE, and it is the following. It relies on a single central authority controlling the master secret key, and all the users of the system obtain their key material from this central authority. If somehow this master secret key gets stolen, then no security is left in the system. And to avoid this issue, a model called Decentralized Multi-Authority ABE has been proposed by Jace in 2007. And this enables the following. So it allows multiple authorities to concurrently manage the keys for the disjoint set of attributes that they control. How does this system work? So at the beginning, there's a global setup algorithm, which is run for one time, and global parameters are generated. Now, each authority using these global parameters can generate their own public keys and master secret keys for the attribute they control. Over here, we are just going to consider the simple case where each authority controls a single attribute. So the CS department just controls CS attribute and so on. Now, what does the encryption look like? So as before, anyone can encrypt a message in the system corresponding to a policy. All they need is the public keys of all the attributes that appear in this policy. Okay. And the keygen algorithm is going to be a little different. Now, consider that the first user has these attributes CS and professor. It goes to both the authorities independently and requests key material for decryption for these specific attributes. It obtains one key each from both the authorities, and this forms its decryption material. Over here, crucially, both the authorities don't need to interact with each other, so they can issue keys in a non-interactive way. What enables this non-interactive key issuance is that each user is associated with a global identifier, which we call as GID. So the first user has a GID1 and it obtains key from CS with respect to this GID1. It obtains another key from the professor authority with respect to the same GID1. And this GID ties together both the key materials of this user. And next, the decryption can proceed as follows. It can use both the decryption parts together to decrypt the ciphertext. And similarly, other users who don't satisfy the policy should not be able to use their own keys to decrypt. Similar to the central ABE setting, we do require collusion resistance against collusion of two users. So these two users with GID 2 and 3 should not be able to combine their decryption material to decrypt the ciphertext. But more importantly, we need to handle even more complex style of collusions over here. In particular, we allow even the authorities in the system to get corrupted, and we require that a collusion between authorities such as professor, EC, student, and users such as GID 3 and 4 should still not be able to decrypt the ciphertext. Intuitively, the reason is none of them have the attribute CS department, so it should not be possible. And addressing this, yeah.
But if the CS student was in this collusion, then they can always cheat. Right?
Yes, then they can, and we don't argue security against such a collusion.
I mean, it's also theoretically possible to prevent that.
Yeah,
right?
exactly. Yeah. So this is the best we can hope for. Intuitively, what you should think of is, all the authorities that are corrupt, their parts of the policy can always be satisfied. And for the remaining policy, as long as the users don't have the sufficient number of sufficient attributes, then you can't win. Okay. So addressing this critical aspect of corruption of authorities, previous work has formalized various models such as no corruption, static corruption, and adaptive corruption of authorities. And in this work, we consider the full adaptive security model. Intuitively, this means the following. At the beginning of the game, the adversary obtains some global params from the challenger. After this, it can issue the keys of the following kind in arbitrary order for any polynomial number of times. The keys are like, it can request authority setup for some authority U. It can request that give me a key for this GID from this authority U. And it can also ask that corrupt this authority U. Just briefly, I want to also mention, maybe I did not earlier, that U synonymously denotes the authority as well as the attribute, since there is just one attribute per authority in this simplified setting. And so, the adversary can obtain the appropriate responses immediately. And after this, it can issue the challenge ciphertext query consisting of two messages, 0 and 1, along with a policy, and gets back message B under the ciphertext, where B is the challenge bit. After this, the adversary is allowed to again make arbitrary many queries in any sequence it wants. Eventually, it outputs a guess bit B prime, and the adversary wins if B is equal to B prime, subject to this admissibility criteria that for each GID, the issued keys plus the corrupt authorities should not satisfy the policy. Okay, so now that we understand what MA-ABE security looks like, let's look at what's the state of the art in MA-ABE. Lewko and Waters proposed the first truly decentralized MA-ABE scheme and used dual system encryption techniques to prove security. Their scheme supports Boolean span program as access policy. But they are only able to support static corruption of authorities. Another downside of this scheme is that they can't support attribute reuse. Intuitively, attribute reuse means that attribute A in this example should be allowed to occur more than once in an access policy, and they can't support this kind of attribute reuse.
Oh, now I have a question. So typically in the attribute formula, it's only and or.
Yes.
Okay.
So Boolean span program captures monotone Boolean formulas. So ands and ors are subsumed by this policy class.
Okay.
Yeah.
So I mean, this can all be sent to like both CS, like students and CS people, like professors, like for like attribute reuse.
Yeah, so you can think A is CS, and I can, for a message, I can say this message should be accessible by anyone satisfying the following. Either it's a CS and professor, or it's a CS and student. So this work of Lewko does not support such kind of access policies.
So it must be this DNF form or some. I'm not sure because this formula can be written as A and B or
Yeah,
C.
sure. So there might be ways to simplify this.
So if you write it into that way, that means this scheme can spot that type of formula.
Maybe, yeah. So I was a little hand-wavy around this specific example. I just wanted to highlight that if it occurs 2 times, like in this DNF form, after such a conversion, like if you can't make this and it still occurs 2 times, then we can't support such policies. Yeah.
What is the significance of static corruption?
So static corruption essentially means that the adversary declares at the beginning of the game that the following authorities are corrupt. After this, it can't make any corruptions. And this model is like not realistic in real world, right?
Okay.
Yeah. So given this decentralized and dynamic nature of MA-ABE, like static corruption is like very unsatisfactory, and it has been a long-standing open problem to handle adaptive corruptions. And for more than a decade, this question was open. Only recently, this work of Datta, Komarbudsky, and Waters showed how to support full adaptive security. And a subsequent work of Chen et al. Also shows how to support attribute reuse in the system. But the proof technique in these works is quite complex, and it uses something called as dual system with dual subsystems. Due to the complexity of this technique, the resulting system is quite inefficient compared to Lewko-Waters. And thus, the central question that we ask in this work is, can we design a fully adaptive MA-ABE without using these 2 subsystems? We also ask a second question. So all the works so far have explored MA-ABE for some Boolean model of computation. And we try to study, can we design any kind of MA-ABE for an arithmetic model of computation? And our contributions are as follows. So first we show that this scheme of Lewko-Waters can in fact be shown to be fully adaptive secure. Towards this, we provide a new security proof, which is simpler than before, and it results in a tighter security analysis. And as a result of this advancement, we observe that both the communication and computation costs are significantly better compared to prior work. Secondly, we show a MA-ABE scheme for arithmetic span programs. And in this construction, essentially, the construction builds upon our framework for Boolean span programs, and we are able to support adaptive corruption of arbitrary many user secret keys. In terms of authority corruption, we do support adaptive corruption, but this comes with certain restrictions, which we feel are due to some fundamental barriers for supporting ASP in the multi-authority setting. Let me briefly talk about what's the communication and computation improvements. We measure communication costs in terms of the number of group elements. And for the policy class of BSP, we observe that across all the parameters, we have shorter sizes. In particular, the user secret key is 3x shorter. So the prior work required 6 group elements in the second source group. Our work requires only 2 group elements. Similarly, the ciphertext size is 1.5x shorter. And our construction for ASP essentially has sizes which are about 2x more compared to our BSP construction.
So why the BSP 2 lines of this work?
So the difference is in attribute reuse.
The cost seems to be the same.
Yeah, the class is the same, but this first work of DKW23 supports BSP with respect to like certain restrictions that an attribute can't occur more than once.
Yeah, I know that. So, but like this work, the 3 lines, the top 2 lines seems to be the same except for the attribute reuse.
Right, yeah.
This line like better.
Yeah, so crucially over here, I want to note that all these instantiations are from SXDH assumption on prime order pairing groups. And the numbers turn out to be the same because we are considering instantiation from SXDH. If I consider like this decisional linear assumption for like k greater than 1, then the numbers have some distinction between attribute reuse or not. So in general, there is some distinction, but for the SXDH, we are able to get the same numbers.
Can you define ASP?
Yes.
What's the modulation?
Right. So let me just let's see. Yeah. So ASP is defined as follows. It consists of 2 matrices, M and N, and a mapping function rho. So these matrices consists of n number of rows, and the mapping function maps rows of the matrix to an attribute. And we say that a set of attributes Z satisfies this policy if this unit vector 1 followed by zeros belongs to the row span of Z sub rho x times mx plus nx. Essentially, it's generalizing from the Boolean span program. The Boolean span program only has one matrix M, and this, instead of arithmetic value Z, it just has an indicator bit 0 or 1, denoting whether I can choose a row of M or not.
Okay.
Crucially, the arithmetic span program subsumes arithmetic branching programs, Boolean span programs, Boolean branching programs. So it can support more than just Boolean span programs. And essentially, like, since there are these 2 matrices M and N, that results in this 2x higher communication costs.
So in this case, what does it mean by the variable is reused?
So in the arithmetic setting, we don't consider variable reuse. It's only defined in the Boolean.
Okay.
Yes.
So for the this attribute reuse, if I don't care about performance, can like a party just like an authority just simulates like multiple attributes. So every time you use like a clone of them.
Yeah, so you can yeah, you can do that. So yeah, at the beginning of the system, you can specify in like in some system parameter that I want to create up to D number of clones, and then attribute authority controlling one attribute can generate D number of master keys and use the first one to issue the first time, second one to issue the second time. But this will result in this blow up in communication and computation by this factor. So attribute reuse essentially asks, can you do this without such a blow up? Right. Yeah. And also in terms of computation costs, our schemes for BSP have faster encryption and decryption algorithms. And over here, we are measuring compute in terms of number of exponentiations and number of pairing operations. Since these are the ones which are most expensive in the pairing groups. The most important thing is in terms of decryption, we require 2x fewer pairings. This results in around 1.7x faster decryption time. So now that I have given an overview of the MA-ABE setting and what are our results, let me share some technical details of how our construction works. Towards this, first I will review the Lewko MA-ABE scheme and talk about what are the limitations in supporting adaptive corruptions. So I have just this slide to recall what Boolean span programs are. We briefly already discussed the arithmetic span program. Boolean span program is a subclass of it. So over here there is matrix M, row, and a string X defines a subset of attributes, and we say that it satisfies the policy if it belongs to the row span of the rows selected by this string X. So X sub row I equal to 1 means selecting a row. Equivalently, it is saying that the attribute U sub row X is in this set of attributes. Next, for secret sharing schemes, there are two algorithms that we use, a share and a reconstruct algorithm. The share algorithm secret shares a secret S and outputs n number of shares lambda 1 through lambda n, where n are the number of rows in this matrix. So ith share corresponds to the ith row. And we can reconstruct from lambda I is the secret S if and only if the policy is satisfied by the shares. Next, let me briefly recall what are composite order pairing groups, because these will be crucially used in our security proof. They are similar to prime order pairing groups with the distinction that they are of order n, which is a product of 3 primes in our case, P1, P2, and P3. There is a bilinear map E from G cross G to GT, and there is this bilinear operation E of G comma A raised to, comma G raised to A comma G raised to B is same as E of G raised to AB. Crucially, there is an additional property that the subgroups GP1, GP2, and GP3 of orders respectively P1, P2, P3 are orthogonal to each other under the map E. What does this mean? For example, E of G1 comma G2 is equal to 1. So essentially, the exponent just vanishes disregard of what the input exponent was, where G1 and G2 are from the two respective subgroups. And with this, let me present what's the Lewko construction. The global parameters consist of the group description and two additional parts, G1, which is element of GP1 subgroup, and a hash function which maps arbitrary strings to the full group G. If an authority controlling attribute U wants to run a setup, it can do the following. It chooses two random values alpha and y in Zn, which constitute its master secret key, and the public key is of the following form: E of G1 comma G1 to the alpha comma G1 to the y.
Wait, is there a reason why you present this in the composite pairing groups instead?
Yes. So
Simpler.
yeah, so to understand the security proof, we use this dual system encryption technique, which is very easy to follow in the composite order groups. But translations to prime order exist, and in our paper, we also show the prime order instantiations.
Okay.
Yes. So the keygen algorithm works as follows. So suppose a GID wants to get a key for attribute U. It can the authority can issue a secret key of the following form. It is G1 to the alpha times hash of GID to the y. Next, the encryption algorithm takes as input this access policy m comma rho along with a message in the target group GT, and it outputs ciphertext consisting of the following terms: C0 and C1x, C2x, C3x for all x in n, where n is the number of rows. So what's the structure? The structure is as follows. We choose a random S in Zn, secret share S into n values lambda i's. We secret share 0 into n values omega i's, and the encodings are then as follows. C0 essentially masks the message with an encoding of the secret S. C1x, C2x, C3x are essentially just Elgamal encryptions of lambda i's and omega i's, which I denote with lambda x square bracket S, just to denote that it's a secret share of S. And why we have this encoding of omega, it will become clear for security proof in the next slide. But the general idea is the following. If a decryptor has attributes that satisfy the policy, then it will be able to recover S from these lambdas and then unmask the C0 part to recover the message. In a little more detail, the decryption works as follows. It takes this product of three values, C2x, C3x with hash of GID divided by C1x. You don't need to look into the details. The crucial part is if I have a decryption key for the xth row, then I can recover this partial value d sub x, which encodes lambda x in the exponent and omega x in the exponent. Now, if the policy is satisfied, then I can run the linear reconstruction algorithm in the exponent itself and get S and 0. And the second term just vanishes because it's a 0. And thus we can recover the message as C0 over D. Okay. And what's the intuition for security? The intuition is as follows. Consider a very simple policy A and B. In this case, the shares look as follows. Lambda A and lambda B are such that their sum is equal to S, and omega A and omega B are such that their sum is equal to 0. And consider that there are these two users with GID and GID prime who have keys for attributes A and B, but not both. Okay. So both these users can recover the respective partial parts for lambda A omega A and lambda B omega B. But now if they try to collude together their parts and recover the secret, this fails because this hash of GID and GID prime is not the same, and thus the omega parts won't cancel out and lambda is hidden. So this is the purpose that these omega shares serve, to prevent collusion between users. On a little more technical level, the proof technique this work uses is called dual system encryption, which was introduced by Waters in 2009. In this technique, two forms are considered for the ciphertext and user secret key, normal and a semi-functional form. The idea is that the normal secret key can decrypt both normal and semi-functional ciphertexts, but the semi-functional key can only decrypt the normal ciphertext. It can't be used to decrypt a semi-functional ciphertext. And the way this technique is used is roughly as follows. We start with a real world where the ciphertext and all the user keys are in this normal form. And then in a step-by-step way, we transform all of them to semi-functional form. So we first modify the ciphertext to semi-functional. Then one key at a time is transformed to semi-functional form. At this point, since everything is semi-functional, so none of the user secret keys can decrypt the ciphertext. So what we can do is simply make a hop at the end in the security proof where we change the ciphertext to encrypt a random message. This is because neither of the ciphertexts are decryptable anyway. And that's the high-level idea. Well, what's the limitation? Why this?
So what is the semi-functional key or the ciphertext in this context?
So I will describe it next. Just wait for a few slides. But essentially, the high-level idea is that this ciphertext is completely in this first subgroup in the normal form. In the semi-functional form, it will span the first and some other subgroup. Specifically, it will be the both second and third subgroups as well. And while these subgroups don't interact across each other, like P1, P2 don't interact with each other, but P1 interacts with itself. So when I add some second subgroup parts to the key, then I have additional multiplication terms that show up in the second subgroup, which disable decryption.
Okay.
Okay. Right. So what's the limitation? Why this proof only supports static corruption? The reason is the follows. When they make this hop from the penultimate step to the last step, changing the ciphertext to encrypt a random message, the work of Lewko Waters actually relies on a target group based computational assumption. And over there, the reduction embeds this challenge in the public keys of honest authorities. So for the reduction to work, it needs to know which authorities are honest and which are corrupt. That's why they can only support static corruption of authorities. Now, towards adaptive authority corruption, what we want to do is make this step information theoretic instead of relying on a computational assumption. Our idea is as follows. We want to break the correlation between these two parts of the ciphertext, C0 and C2x, which contain this S in the exponent. So C0 has this secret S and C2x contains secret shares of S. If we can break this correlation, then we can try to use the entropy of S mod P3 to randomize this message. So how are we going to do this? What we are going to do is try to use the entropy of this master secret key part alpha to change the shares of S to a share of some random value. But unfortunately, this alpha mod P3 is information theoretically revealed to the adversary. The reason is the follows. In the security proof of Lewko Waters, this semi-functional form of secret key looks something as follows. It has some third subgroup elements like G3 to the alpha and hash of GID to the Y, along with some other first and second subgroup parts. But crucially, if you just inspect the exponent of G3, it is like alpha plus some Z times Y, where Z depends on the GID. And if the authority issues keys to two different GIDs, then this Z value is going to be different. Information theoretically, both these parts are completely revealed, and thus you can recover Y and alpha from it. So this information is leaked, and this doesn't quite work. So our main idea to make this proof go through is the following. We are going to modify this semi-functional form of the user secret keys such that the information revealed is just alpha plus C times Y instead of alpha and Y completely. How are we going to enable this? We are going to massage the secret keys such that the third subgroup part, this H3, for any GID remains the same. Meaning this coefficient of Y is some constant C, disregard of what GID we are trying to hash. If we are able to achieve this, then across any number of keys issued by an authority, in this third subgroup, the leakage is just alpha plus C times Y and nothing more. This allows some entropy to still be left in alpha, which we can harness to do the last step. Okay, so now that I have given an idea of what's the challenge and how we are going to approach solving this challenge, let me give a quick overview of our construction and exactly how this goes, the proof step goes through. So our construction is going to be more or less the same as the Lewko key. Just we will make two simple modifications. On this slide, I just have the Lewko scheme. The first modification we make is the following. We introduce an additional term in the global parameters, little h, which belongs to the full group. And what we do is, whenever we were taking this pairing between G1 and G1, we replace this with a pairing between G1 and H. Intuitively, this gives me a little more source of entropy since H lies in the full group instead of just an element in the first subgroup. And with this modification, we can appropriately change at other places like the ciphertext and in the key to correctly enable decryption. The second change is this ciphertext component C2X, which was a target group encoding. I don't need it anymore. I can just put it in the source group G1. The reason is that the earlier work of Lewko relied on this target group assumption, where they needed to embed the challenge in this in the target group, and thus a target group encoding of S was used. But we are going to replace it anyway with the information theoretic step. So we don't need to do target group encoding. We can just encode in the source group G1, and the decryption can take care of it by doing one more pairing operation over here. Okay, so not really any significant changes, just two very minor changes, and this is our final construction. And any questions on the construction, or does it make sense? Okay, so essentially just the Lewko construction. So how does the security analysis work? The security analysis uses a subgroup decision assumption for all the computational steps that we need. Let me recall what this assumption is. So the assumption asks to distinguish between element belonging to subgroup G, Pi, Pj from a full group element, given some auxiliary information. this is a very general form of the assumption, and the way I like to think about it is the following. So in this auxiliary information, I can give out anything I want as long as it does not help distinguish between these two forms of the challenge. What this means is I can't give out elements such as belonging to this other subgroup G pk, where k is not equal to I or j. Because if I have an element from G pk, if I pair it with a form of G pi pj, it will just vanish because of the subgroup property. But if T belongs to the full group, then it won't vanish. This third subgroup part won't vanish. So I can't give out terms that help distinguish. For a very simple example, consider distinguishing between full group and the subgroup T1, P2. So over here, I am allowed to give out information of the following kind. I can give out generator G1 of the first subgroup. I can give out generator G2. I can also give out some additional encodings of the following kind: X1, X3 belonging to P1, P3 subgroup, or Z2, Z3 belonging to P2, P3 subgroup. Well, you may ask, why am I doing this? Intuitively, the reason is the follows. If the reduction needs to somehow simulate elements of the third subgroup, while it can't get access to GP3 elements like this, but it can use elements of this kind to simulate the third subgroup part. Like X1, X3 contains some information in the third subgroup. So it can use elements of this kind. And crucially, these elements don't help distinguish, because in the first case, the GP1 subgroup does not vanish. In the other case, the P1 and P3, both subgroups don't vanish. Okay. In our work, we actually use a new version of new variant of the subgroup decision assumption, where compared to this third subgroup part Y3, which was independent of the auxiliary information, we claim that in fact it can just be X3, which is present in the auxiliary information. And why this works? The reason is that we can just reduce it to the original subgroup decision assumption that we just saw. So say we start with a form T1 times T2, then we use the subgroup decision assumption to go to T1, T2, Y3. Now I can imagine Y3 is just a product of two values, U3 times X3 for some value U3. Now I can again apply the subgroup decision assumption only on the T1, T2 times U3 part to remove the U3 term. And then I will be just left with T1, T2 times X3. Crucially, what this will help us with is that if we consider multiple instances of this challenge, the X3 part can remain the same across those challenges. And this will essentially help with this idea that when I'm computing hash of GID, I want that across all the queries, the third subgroup part remains the same. That's where I'm going to use this assumption.
Is U in the third group part?
Yes. Yes. So whenever I write 3 below, it essentially denotes it's in the third subgroup.
Actually, I did not get why the third step using this subgroup decision assumption can work, because there is the X3 in the third group,
Right,
which is not the case in the original assumption.
right. So what you can do is observe that the auxiliary information contains X1 times X3. So the reduction obtains a challenge, multiplies it manually with X1 times X3, disregard of which form the challenge is in. And thus I additionally get a X3 term.
I understand.
Okay. And yeah, as I said, this style of assumption is crucially used when I want to modify this hash output to be the same across all queries. Okay. Now let me spend a few minutes just to give an idea of how this proof works. It follows this dual system technique where I will keep using this subgroup assumption to introduce some terms in the other subgroups. And the idea is as follows. So, okay, we begin with this hybrid 0, which is the real world, where everything in the ciphertext lies in the first subgroup, and the user secret key lies in the full group G, and it's a product of two values, some alpha and some y dependent term. Okay. For the proof, just to simplify our understanding and focus on the important parts, we won't worry about the alpha. It is going to remain same across all the hybrids, and I can always simulate it. I will only worry about the y dependent parts. And also, I will only talk about what happens in the exponent. Okay. So let's just focus on what's in the exponent. C0 has S, which is being encoded. C1 has R. C2 has lambda plus something, which is the Elgamal encoding. But for the moment, I want you to forget about all that. Just it's a secret share of S. And C3 has secret shares of 0. And over here, the hash of GID exponent is like some Z sub GID multiplied with Y. Okay. So the idea is as follows. There are 8 hybrids. I don't think I have the time to go over all of them. So I will just mention the key ideas. The idea is as follows. We introduce terms in some other subgroups in a step-by-step way to modify to this semi-functional form. What it will help us with is introducing some stuff in the third subgroup of ciphertext, which will have entropy to randomize the message. That's my eventual goal, somehow to introduce this term. But it requires some care because you can try to decrypt ciphertext using keys, and if say second subgroup parts are present in both ciphertext and keys, then they start interacting with each other. So what we first do is change the hash output from the full group to just the first subgroup. And crucially, this just relies on the subgroup decision assumption between G and just GP1. Over here, just as a sanity check, I'm not allowed to give out encodings of GP2, GP3, or GP2P3, but this is okay. Since what I'm going to do is the subgroup decision challenge will be embedded across the keys, and I can simulate all the ciphertext parts just in the first subgroup. And first subgroup I'm allowed. I'm just not allowed second, third, and 2, 3 combination. Okay. And then once we are at this point, in a step-by-step way, we start introducing these terms in the third subgroup. So we copy from the first subgroup to first and third subgroup in the ciphertext. This again relies on some subgroup decision assumption. And without going into too much details, what eventually happens is some second subgroup encodings also show up. And after we have some second subgroup encodings, we modify the hash output to be across the first and the third subgroups. This step is a little involved. So this step needs to occur one key at a time. And even for each key, there are 5 inner hybrids that show up. So I'm not going to give any details of that. It's some standard technique that previous work has shown how to use. Though what's the novelty in our work is once we have reached this hybrid 5, where let's see what we have. In the secret keys, disregard of what GID it is. In the third subgroup, I just have a coefficient of C. Okay. And in the ciphertexts, I have encodings in all first, second, and third groups. Crucially, though, the encoding of omega is shares of a random value, not shares of 0. What this will allow me is the following. I can change these shares of S prime prime, which are correlated with S prime prime in the C0, to just shares of a random value, T prime prime. And we claim that this is an information theoretic step, relying on just two facts. One, that corrupt rows are unauthorized, and second, that the structure of secret keys is of this specific form. Well, how this works is as follows. So what we do is, if we want to modify shares from S prime to T prime, we essentially enable this by modifying alpha to some other form, alpha plus some delta, subject to the constraint that alpha plus C times Y is information theoretically revealed. So I also need to modify Y to some Y plus like 1 over C times the same delta. What this means is the shares omega are also switched from W prime prime to some other value V prime prime. But we argue that this is okay because both these values are just uniform random and hence identically distributed. In essence, making this switch over alpha and Y, which are the parts of the master secret key, allows me to break this correlation between S prime prime and this C2X part. Now, once we have reached this point, the last step is just that C0 is going to encode a random message. And to argue this, we just rely on entropy of S prime mod P3, that this information, it is information theoretically hidden. So this completes the technical parts of my talk. I did not have time to go over all the details. I encourage you to look at the paper. Crucially, what I did not talk about are the following. So for the DSP construction, I did not talk about the inner hybrids. I did not talk about the pairing group instantiation and the extension for attribute reuse. Also, I did not talk about the ASP construction, but in essence, ASP construction just follows our BSP construction. It just uses two copies for this matrix M and N. And I'll leave you with two open questions. One is, as I alluded to earlier, the ASP construction, we can't support full adaptive security, and it's an open problem how to achieve this. We are only able to support corruptions with respect to with some restrictions, which we feel are some fundamental barriers, and it would be nice to get a positive or a negative result. We don't have a proof that the barriers are fundamental, but they do seem like it. The second is all the constructions in our work and the previous work that I talked about today are in this small universe setting, which essentially means that the universe of attributes is predetermined at the beginning to be of some polynomial size, and the system parameters depend on this. Large universe MA-ABE asks to build constructions where the universe of attributes is exponentially sized, or in other words, the system parameters don't depend on the size of the universe. And this is a long-standing open problem. We don't even have any constructions from standard assumptions. All the constructions that we know of are either from some Q-type assumption or in a GGM model. Yeah. Yeah. Thank you. Questions?
Uh, Yeah.
Is there other kind of like applications that you will introduce assumption and the subgroup?
We haven't thought about other applications.
So like you develop like such assumption like only for like this very like specific like constructions. Something.
I'm not aware of yeah, I'm not aware if this assumption can be used in other places. Like in a sense, it is just the standard subgroup decision assumption, which we just massage in a nicer way to show this. I wouldn't say the assumption is any interesting. It's just a different abstraction to explain how can we switch these third subgroup parts of different user keys to share the same value.
Thanks.
So can you emulate the ASP model with the BSP model with some blowout?
Yes, so you can do that.
So basically the open question is like whether you can do it with some
Right,
efficiency.
right. Yeah, I should have mentioned that. Yes. So, yeah.
Do you know of any practical deployments of ABE?
I know that entity research is deploying some ABE. I think Cloudflare has also deployed ABE for terminating, I think, some sessions. Like if users connect online and their sessions get disconnected, how to terminate connections efficiently. So not efficiently, securely, they do it using ABE. Essentially, I think the idea, I haven't looked very closely at their system, but the idea is that since Cloudflare manages web access across different continents, so say if a content should not be accessible in a different country, but it's accessible in the US, how do I enable this for the users? So a user sitting in, say, India tries to access a website in the US, maybe it's not authorized. So they use ABE keys to manage such access labeling.
Yes. And is it multi-authority?
I don't think so. I think it's a central, like Cloudflare manages all the keys, I think. I think Entity is also exploring some applications for, I think they are exploring 2-3 applications, but I don't think they are in concrete deployment at this point.
Well, so let's thank the speaker again.